So thank you, Greg, for giving me this opportunity to come and speak here. So I actually was here on this campus, not in the business school, but out there in the Hearst Mining building back in the 90s. So that's when this building was being built. And then we all came, I remember, to look at it. It was the spanking new building, and it still is really nice. This is a very nice classroom. So my background is a geophysicist, and I ended up as a data scientist through a very strange route. I can talk to you later if you're interested, which involved working at McKinsey for a couple of years, after working in oil and gas for some time, and then kind of getting into software. And then 5 years ago, I joined a company that was making parallel databases called Greenplum. And then that was acquired by EMC, which has been spun out as Pivotal. So Greg tells me that you have already had a lot of exposure to data science. So please feel free to stop me and ask me questions if you want me to go in a different direction, or if you want to go deeper, that's perfectly fine. I will be very flexible about that. So what I'm going to talk about is so a little bit about what I do at Pivotal. So Pivotal, I will describe later on, what we do, but we actually make the constituents of what we call a data lake. So we go to customers and build data lake for them. Now, my team, we basically are the bridge between the customers and the engineering. So traditionally, something like data lake is sold to the IT departments in companies, but the users of something like a data lake are the other business departments. So, and we act as that bridge. We kind of are able to talk the language of both IT and business. But in doing that, we end up going to lots of different companies, finance organization, retail companies, manufacturing companies. So what my job is to create kind of a high level abstraction of everything that we do, so that we can actually have a data science program, we can recruit people. And so that's kind of where I'm coming from. So the one interesting thing is that let's start with the question why, and then I'll go to how we address that. And the question in the broad sense is, why do we need big data at all today? And if you think about it, one of the ways to describe the change that has happened, let's say in the past century, is that the world was much simpler before. So one human being had to deal with a limited number of organizations and communities, right? An employer who was lifelong, Main Street stores where you dealt with things at a human scale and not large organizations. So think if you own a restaurant, right? If you want to introduce a new product, it's very easy. You ask your regulars, what they like, and you introduce something, and within a day you know whether it's going well or not. You know what your competition is. You immediately can react. But for a big company, it's difficult to do that. And for an individual, it's even more difficult. So today's world, more complex, lots of other things that you need to deal with. And you are in business school, you know this better than I do. But for instance, there's just one statistic. So think of travel. So before the First World War, there was no such thing as passports. You didn't need a passport to go anywhere. And even in 1980, it was around 300 million is the order of how many international travelers there were in the entire world. By 2012, it had already crossed 1 billion, so it's probably even more now. So just that one industry alone, and that also means that for the individual, when we think of doing travel, that's an activity that's open to us, which is great. And in general, it's good that the world is more complex in many ways, because again, in 1900, the general life expectancy was less than 40. It was around 30. And today, everywhere, the overall life expectancy is in the high 60s, including, that includes all countries, of course, much more in the developed world. So all this complexity doesn't necessarily lead to happiness. And I wanted to just bring to your attention a couple of authors who have done some interesting work here. Sheena Iyengar is in New York, and she has done this work on the art of choosing, where she has actually shown mathematically using data that just having a bigger assortment actually leads to lower sales. So for instance, you go into a store and let's say you're buying something like yogurt. Unless it's a necessary purchase, if it's milk, you're going to buy milk. Doesn't matter what milk there is, how many choices, how much choice there is. But in discretionary purchases, if there is more assortment, you'll attract more people to the display, but you'll actually sell less. And then Barry Schwartz, he's at Swarthmore, he has a very interesting book on the paradox of choice as well. Oh, really? Yeah. When will he be here? I might come and... Oh, okay. I love that book. So that's great. He will speak about it more eloquently than I can. And then if you think about from the organizational point of view, it's again a huge thing, dealing with complexity. And this is the Macondo, a picture of the Macondo disaster back in 2010. And because I worked in the oil and gas industry, this was really shocking to me and other people in the industry, because we took a lot of pain just to prevent this sort of thing. So what happens in an offshore oil drill is that there is actually a control room where you get on time, real-time information about all the activities that are going on. So there are like hundreds of measurements that come from the production well, including the pressure, the variation of the pressure, temperature, the consistency of the material that's coming out. But the problem is all this information is displayed separately. They're actually collected by different vendors. It's all subcontracted out. And it's up to the team who is sitting there, which is a bunch of humans, right? Very, very technically proficient humans, but they are the ones who have to decide when they feel something can go wrong. And it's always possible for human beings to make a mistake. So the question here, and this is the obligatory Dilbert cartoon, the previous speaker had one too, so I'm allowed one, only one, I promise. So, the thing is that, you can't just address such complexity by calling it business as usual. You can't just say, okay, I'll put easy to use on the list, and that's it. No, that just doesn't work. And therefore, that leads to the whole business problem. The solution is that if we can make systems smarter, then our lives become simpler as decision makers within organizations and also as consumers and citizens. So how do we do that? So this is where I introduce the smart system. So let's look at how the human brain works, because that's where we always go for our inspiration. So just a simple action. You see a baseball player, he sees the ball coming, he analyzes the trajectory of the ball and predicts it, because it's actually not that difficult to predict. It's a deterministic system. Based on that, he decides what action to take. So in that metaphor, there are the sense organs, the limbs, the nervous system, and the brain. And the metaphor is that they're being mapped to sensors, actuators, the network, and the digital brain. So this is kind of the base metaphor for my whole presentation. So any questions on this, if you're not clear? It's pretty simple. The question is how you apply it. So how we apply it is that we actually have all of these things today. We have sensors everywhere, right from a Fitbit to the phone to, like GE, you said, they came and they talked. So like one of their jet engine measures like a few hundred measurements every second. So you know exactly a lot of what's going on. Then there are actuators which you can use to initiate action. There are decision support tools which again, everybody has access to and they're improving every day. But what's missing is the brain. And then the question is, how do we create the digital brain to bring all of these elements together and make the system smart? And creating a smart system is what big data enables us to do. And very simply, what it entails is having the data in a data lake and using data science to build models in the data lake. So let me then define these terms, because these are terms which are very new and therefore they are used and defined differently by different people. And I'll give you my definition, the definition that Pivotal has. Whether that will become the definitive one remains to be seen, right? I mean, we'll know in a few years. So the data lake, again, I think you're familiar with the concept, so I won't go very deep into it. But from the data scientist point of view, we're looking for two things in the data lake. One is it has to accommodate different latencies, which is speed of action. Whether it's in ingesting the data, it could be real time, or it could take a much longer time. So for instance, right now Exxon is working on a way to image the underground using what's called full wave inversion, and their test data set for that is 9 petabytes. So that is not something you really need to ingest in real time. That can be in one place, and because you need to kind of just use it and try out your algorithms on it. But on the other hand, the real-time uses, of course, whether it's the internet or in the example, the motivating example I showed about the oil rig, you need to take action in real time. So a data lake essentially is composed of different types of software which work together. And if you have any questions about a technical detail, I can go down to any level of technical detail, just let me know. But from the data scientist point of view, the second thing is that how to future-proof the data lake, because there are so many tools that are coming up. The innovation in this field is so much that you don't really know what tools will be useful 6 months from now or even 1 year from now. And as the previous speaker pointed out, the important thing in all of this is the question. And the questions also change as your competitive landscape changes and as new products come into the market. So the way to future-proof is to use open standards. So those are the two key features. And the one big advantage of the data lake over older systems is that hardware has become cheaper, as have databases. So what that means that if you go into any organization today, every department has their own data warehouse. So data becomes siloed. And therefore, for the data scientist, there is no one source of truth. So I have seen in most companies, the report for something simple, like say a telco, telecommunication company, they're looking at churn. There will at least be 3 different reports measuring churn in 3 different ways, which don't actually align with each other. And what that does, it devalues analytics for the decision maker, because what do you trust when you make that decision? So what data lake does is that it actually puts all the data in one place, not necessarily physically in one place, but conceptually in one place. The data lake can actually be distributed. You can put it over 2 or 3 different data centers, but it is one data source, and that enables that really makes the job of the data scientist very easy. Just a quick thing, I don't want it to be too much of a marketing talk, but I do want to let you know how Pivotal addresses this. So these are the products that Pivotal manufactures. So on the data processing side, you have a Pivotal version of Hadoop. We also have Spark, which is again an open source project in Hadoop, which works within Hadoop, and Spring XD, which is another open source project which enables you to ingest data. So it's a Java framework. So it essentially creates an operating system which is independent of where you store the data, whether it's AWS or whether it's your own private data center. And then we have a relational layer for doing advanced analytics, which is much faster than what you'd be able to do in Hadoop. And finally, to deploy and build apps, we have a series of tools. So the only one I want to sort of mention a little bit is Gemfire, because that comes from the finance industry where you do automated trading. So that's again a parallel system, but it's in memory as opposed to storing things in the disk, which makes it much faster. But of course, you can't store that much data in it. So depending on your use case, which is the question you ask, you combine these different things to build a data lake which is relevant to your organization. So the important thing about the open sourcing of this is, first of all, Cloud Foundry is an open source. So IBM is building its Blue Mix system, where which is actually they're putting in machine learning into the cloud based on Watson, which is actually based on Cloud Foundry, which was started by Pivotal. So the idea is, so what we are seeing in industry now is a convergence in terms of the different standards and different products. In the same way, there is a Pivotal big data suite, which is Gemfire, Greenplum database, and Hawk, and they're all being open source this year. So we are completely changing our business model to that of a company like Red Hat, for instance, what Red Hat does with Linux. And Hadoop, we already are using an open source, which is Hortonworks and Pivotal together actually have that open source. From a data lake, then I want to move on to data science, which was the second part. And I have a definition, which is a lot of words, but basically there are three things that are important here. One is that mathematical techniques you use are not coming from one department. So half my team actually have a machine learning background. They are computer science PhDs who have done machine learning. The other half are actually from other disciplines: economics, bioinformatics, mechanical, electrical engineering, other quantitative disciplines. And the idea is that a lot of the algorithms and techniques which have been developed for different situations can now all be used because of this, having this big data platform. They can all be used in the same platform. So there's no reason why you should not have all of these tools when you are attacking a new problem. Secondly, you have to be able to use multi-structured data, which means not just data which is quantitative, but so to give you an example, in again that case I mentioned an oil rig. What we notice is that when we go and try to learn how to predict failure, you look for previous instances of failure. Now, when you just look at the sensor data, you see when the machine is working and when it's not, when the drill is going down and when it's not. But you don't know just from that when it's not going down, why it's not going down. Because some of those stoppages are planned ones, some of those are unplanned. And you'd be surprised, you don't get that from one system. So you have to look at different systems, including technicians' notes, which is text analytics. So then you have to do text analytics. You need text, sometimes you need video, and you have to put all of that information together, because what we want is really information irrespective of how it's stored. And then finally, a distributed computing environment is very important, because the moment you start taking data out, moving data, putting it in one system, you're losing the advantage of big data. It becomes much more difficult to use. And then in data science, the other thing is, how do you actually do the project? So this is the methodology that we have come up with. And you can feel free to email me any questions you might have. Have a good flight. So this is based on the CRISP DM methodology, which comes from analytics as it was practiced back in the 90s. But the difference is that we have kind of had to redefine it for big data. But remember that it always starts with problem formulation. And I always also give the example of Kegel. It's exactly the thing, Anthony tells me too that, hey, we don't need domain knowledge. I've had that conversation with him too, because look at all the people who win Kegel, they always come from outside the domain. Yeah, but that's because you have formulated the question and you have created the right data set. Because those are the two things that actually take the most time in this cycle. So typically what we do is a 3-month project where we go across this cycle, and within the 3 months, at least a month is taken in these 2 steps, sometimes more. Sometimes it's half the time. So the problem formulation is where you need to bring the people who understand the data and the people who are going to use your answers together. Because otherwise you can have a mathematically very successful project and it will be completely useless in terms of ROI, because no one will use those results. Then the data step. So this again is very different in the world of big data as compared to what it was last century, where you would use software like SAS or R, because there you deal with maybe 100 features, and you end up with a model with 15 to 50 variables. But now you're dealing with thousands, hundreds of thousands of features. Because just think of video, right? How would you actually featureize video? You have to look at frame by frame and then look for anomalies to, for instance, to detect intrusion. And you need to have the right tools to do that. Once you have the problem and the relevant features, finding the right modeling technique is almost trivial, because the algorithms are very good nowadays and there are always new ones coming out, like deep learning is the latest thing, very good for video and text data. Once you have that, then the application actually does require a lot of thought as well. This could be something really simple, like spitting out a set of numbers like predictions in a CSV file, which then people can ingest in any software to look at. But it could actually involve building a custom application. So for instance, what GE has done, and we work with them, GE actually owns 10% of Pivotal, and the rest is owned by EMC. So we are still a privately held company. And we work with GE on their big data platform called Predix. What they do is they have different applications on Predix. One of them is for a technician who is called to repair an offshore GE product installation. They do a lot of stuff for oil rigs too. So when the technician is there, he can actually open up his iPad and he gets predictions and suggestions for what to look at based on the big data model, back in the data center, in the data lake. And also then he can see, he can put in what he's seeing to fine-tune those recommendations, and he can actually even take pictures with the camera and send it back for remote matching. So think about that, that's a very sophisticated application, and this is where the gap is today in terms of data science. We have very nice models, but often the gap is in applying those models. And 4 other things, that kind of are complementary to these 4 phases. One is technology selection, because remember, a data lake is a data platform. It actually, you can install a lot of different tools there, and you might need different tools for phases 2, 3, and 4. Then iterative approach, you need to be agile. We do a feedback session with all the stakeholders after every phase, and based on that feedback, we sometimes have to iterate. Then there is creativity. So this is again, the question of the use case and the ask, right? So there is a set of asks which are standard, which every company does, and we all know about it. And we can make those better. We can add new data sources or fine-tune that question or build a new application for that. But there are also completely new asks, like when we're talking about the Nest application. So once that's there, you can see there are so many other things you can do. And I'll talk a little bit about some work I've done with Silver Spring, who are in the Bay Area. They're one of the main manufacturers of smart meters in the world, in the utility industry. And with Silver Spring data, the data that you get from smart meters, you actually get the pulse of the entire city. You really know what's going on. You can basically map economic activity and business activity, because most of the things we do use power. And then, finally building a narrative. So there is an organizational aspect to this whole technology, because this technology is still in the stage where it's moving from being cutting edge to state of the art. So it's moving beyond early adopters at this point. But in an organization, you still will find some people who have done analysis using SAS for many years, and they don't want to learn new things. They're comfortable in their world. So you have to find early adopters. You have to get them excited and do a project and use the results of that project, to get more adherence. So building a narrative is actually key part of this process. Now, in terms of the toolkit, again, technical stuff, so I won't go deeper into it unless you have questions. But the key point here is that try to pick something that works in parallel, because that's how you'll be able to get the advantage of big data. Otherwise, you are stuck using an old tool. Now think about applying that to this problem, the oil rig problem. So what we found that if you take all the data for one oil field, you can build a model for predicting the rate of penetration of the drill. Once you have that model, you can then run it. You can score that model in real time and compare with the actual rate of penetration. And when you see that moving apart beyond the threshold, it's an anomaly. So you raise the alarm. You label those anomalies, while you are after building the model, so you know what sort of action to take. Whether it's just an alarm on the screen, or you need to even send an alarm to a larger number of people, including to people's cell phones, or whether it's just a question of, or even that if it's so dangerous, you might want to actually shut down the whole system. So right now, when this system is being used, people still don't trust it enough to actually enable it to shut down the whole system. So that's still in the future. So right now, it is mostly used for aiding human beings. It's not replacing human beings. So when I talk of smart systems, that's something to remember. That like for instance, today's self-driving cars, a lot of the things, the ultimate aim is that you can move the human being from the equation, but I am not seeing that happening at this point. It will probably happen in the future. This is the one about smart meters. So here what we did was we see this data sets, this time series data from every smart meter, and simply use Fourier transform. And the reason I put that here is that that's again a technique that comes from physics and electrical engineering rather than machine learning and computer science. But it works, and it enables us to extract the right features. So for instance, a household, for instance, has 2 cycles per day on a weekday, because people get up in the morning, power usage goes up, then they go out to school, to work, and then they come back home and power usage goes up again. On the other hand, a school or a workplace, has 1 cycle per day. And then a big retail space will have a weekly cycle, because much bigger power usage in the weekends. So you can completely automatically detect all that just by doing a Fourier transform, where again, if you do it in a parallel system like Hadoop or Greenplum database, you can transform, a whole city's time series, say 2 years worth of data in a matter of minutes. So it's very easy to experiment and play with that and build the right solution. And then, you actually have to build a solution where it's integrated into the utilities system of maintenance and repair. And only then you get ROI. So as I said, the data science project itself takes 3 months, but there is the data collection part and before and the operationalization part after. So something like that would very easily take 6 months to actually get real value out of and going beyond the stage of a pilot.
So we had a speaker come from UPS who talked about their Orion system, and one of the big challenges they face is that the drivers were initially suspicious of the instructions that were provided by the system. How do you overcome the human factor in implementation of digital brain-like decision making?
Yeah, and we actually see that a lot, and the answer is not a pure technological answer. So we have to treat this as an organizational transformation. It is not just buying a software or hardware and plugging it in, which means that we need to get the users and representatives of the actual users into the process right from the beginning, so that they become part of the problem formulation and we address their concerns. And it's a real thing. It's not just something we need to do to please them, but sometimes they bring up very good points, right, which are details about the way they work, where we need to design the system correctly. So in Pivotal, what we do is that there is the data science team. So we work closely with the development team, the app development team, who are a completely agile shop. So we actually bring in the user community into our lab for the duration of the app building, which could be like a month. And we work together with them so that the whole thing is very transparent and it's not a black box. And we give them several kind of prototypes before finalizing the actual app, so that it has already been used by a few people. And when people see that, when they see, oh, some of the drivers are using it and our people are using it, that helps a lot in overcoming that. But still, it's not instantaneous. It takes some time. Any other questions? So is this something that you have seen, or is this, is there anything that is new? Because I don't want to spend too much time on things you have seen. Okay.
Can you remind me the Fourier transform?
Yes.
Transform is transforming. What type of data into?
Right. Yeah. Good point. I shouldn't take that for granted. So the time in any time series basically is so we're looking at utility data. So we're looking at the usage, power usage in a smart meter at 15-minute intervals in this case. Sometimes it's 15, sometimes it's 30. So you have the whole pattern over the period of, let's say, a year. So what the Fourier transform does is that it extracts the frequencies in that system. So it will say the dominant pattern in terms of frequency is that you see a daily cycle, and there is another pattern which is maybe a weekly cycle. And usually there is also a seasonality, seasonal cycle, summer, winter, depending on temperature, there is a change. So that's what the Fourier transform does. And it's from 18th century, I think. So it's a pretty old technique used in physics for a long time, but we are able to use it very effectively in this case. Interestingly enough, the other ways where this is used is in compression. So for instance, the JPEG format for storing images also uses the frequency, because you can take a whole time series and it's compressed. If you're just able to store the frequency and then convert it back to time. So it's not just about time series. You can even use any sort of spatially distributed data as well for that. So these are some of the use cases. We were talking about in the earlier talk about how to get the asks. So when Silver Spring came to was 4 years ago, they were one of the first people with smart meters, and they were like, we have all this data and we can do billing very well, but what else can we do? And I didn't know the answer to that either. So I went with them to actually different utilities. So we actually did workshops where we brainstormed and got use cases which would have business value and which could actually be solved by that data. And the basic technique that I showed is the same. We use the frequency elements in the time series of power usage to cluster the data. So we have, then micro clusters of users, and based on that we get a lot of information, and also we monitor that. And when things change, when people start behaving in a way that's no longer typical of their past usage, then also we know something has changed and we can act according to that. So the other interesting thing is that we did was with a Canadian company. So for them, the power theft turned out to be something that we don't see in California. It's about growing pot, because they need a greenhouse to grow pot. And funnily enough, the power company doesn't really care about who grows pot, but the people who are growing pot, and it's actually, you can make a lot of money there because it's still illegal, they were also stealing power because they were afraid of being caught. If they'd actually paid their power bills, they actually wouldn't have been caught. And I guess the ones who are doing it are not caught. But so that really was a very high ROI project. Something completely different, where big data is used a lot is what's called advanced persistent threat. It's a cybersecurity problem. So if you think about it, there is a pattern to these threats, right? It starts with phishing, then where a handful of users are targeted, then the user machine is accessed remotely, and then they use that machine to acquire data and then attack and take the data out. So here what we do, we call it anomalous. It's basically we use an anomaly detection algorithm. So there are two ways, to solve this problem. One is what companies like RSA do, where they have specific threat signatures that they look for. The other is the big data approach, where we are just looking for normal behavior and establishing what is normal behavior, so that when things change, we can flag. And we use a graph mining algorithm here, because the usage, the connections between the different machines in a network creates a graph, so the same techniques that you can use for a social graph, say that you get from Facebook, can be used here. And you are able to see how the different clusters of people, because normally machines kind of behave. You are using a machine in an organization. You are accessing a certain number of machines, and of course there is the email server, which everyone accesses, and that's different. But so you can establish all those patterns and then kind of see when there is an anomaly. But the underlying principle remains the same. You are essentially putting the data together to build a brain which can see what is normal and what is not, and based on that it can take action. The other one, again, completely different. So Greg, let me know about the timing, when there is...
We got a hard stop at 4 o'clock.
Okay, right. So this one is about financial compliance. So because of the new laws on the financial organizations, it's kind of very difficult for them to even know whether they're complying or not, because it actually requires them to know in depth what's going on. So we are working with a lot of them and essentially doing a lot of, pattern detection to see what is the normal pattern. And based on that, then we can check with the rules to see if the rules are being violated or not. And sometimes people violate rules inadvertently, so we warn them, look, this is not right. And sometimes, we can see that there is a persistent and a regular pattern of rule violation, in which case it becomes a bigger issue. But again, a lot of the time is taken in terms of doing the data cleanup and text analytics. It's a very heavily text analytics based problem, and really the key here is providing a flexible user interface where it enables human beings to see the anomalies and kind of sometimes there are false positives, right? So they kind of point out, and then the system learns from that and gets better with time. Funnily enough, a lot of the investment in this area is because the banks actually need to show to the regulator that they're actually doing things. So in some ways they're being kind of forced to kind of implement these systems, but they actually, of course, are useful. So quickly, I wanted to show you how a simple sentiment analysis engine works in terms of the data lake. So Ganip, which has now been bought by Twitter, sells Twitter data. And if we subscribe to the Decahose, it's about 55 million tweets per day and growing. So then we get it into the data lake. Spring XD is the framework for ingesting the data, because you have to ingest it fast, otherwise they will shut off the hose if it piles up. Then it's stored in Hadoop, which is, does everyone know what Hadoop is? Or at least is, okay, good. So it's stored in Hadoop, which is now the standard really for big data. And then we we ingest it into Hawk, which is our parallel database, but it runs on Hadoop. And we use a version of Python called PL Python. It's an open source version of Python developed for Postgres, which is an open source database. And then we do two types of analysis. One is a topic analysis, and the other is a sentiment analysis. And then we have built an app with a few, again, open source components where it can be constantly monitored. So this again is different from the way people were looking at social media even like a year ago, where they would get regular reports from agencies about what is happening to the sentiment, because this is a real-time and automated system for continuous monitoring. Then finally, the question is, you can do data science projects and have positive ROI, but how do you really make sure, what is the big picture? So this is from Michael Porter's article in Harvard Business Review in November, where he talks about how the Internet of Things is affecting business. And this is an example he gives from a John Deere tractor. So the first phase is transferring a product into a smart product. You put sensors in it, and you can put some intelligence within the product. But then you connect the product, and that takes it to a completely different level. So essentially, then it becomes part of a product system. So you have a farm equipment system, which has the tractor, the planter, the tiller, and the harvester. And so what we found out is that today the way farming is done is so amazingly information based. So for instance, this farm equipment system, it determines, you give it the plan, the farmer tells it what to do, and it takes in inputs. So it takes in seeds, it takes in pesticides and other chemicals to counter the effect of those things, and it goes and digs a hole, puts in the seed at a particular depth, and measures the moisture content and all of that. And it actually is connected by GPS to make sure that it's putting it in the right place. Now, the other sort of side thing about it is that what does the farmer do in that situation? The farmer really doesn't have to go and do backbreaking work in the field anymore. So the farmer tweets. And we did a project where we saw that from looking at the Twitter content, we can get some information about corn and soy futures prices before the stock market incorporates that. So it's actually very, very interesting. But again, that was last year. So by this year, if enough people are using that information, it's no longer of value. And then finally, you connect it to a system of systems where, and this is the thing which doesn't really exist in most industries yet. So most of the work right now is in this area. At least that's kind of the type of stuff my team does. is actually creating systems of product by using smart connected products. But for an organization, the challenge is to do that in a continuous basis. You get data, you do analytics, and then you build apps, and you have to keep doing that cycle continuously. And for that, that is really what we work with our customers to do. Because either you could outsource all of that, or you could, try and do that in-house. And usually it's a combination of the two. So here, what matters is platform, process, and people. So platform is what I talked about already, the data lake. The process is that you need a roadmap. You're not immediately going to become a data-driven organization. So you start with sense and respond, and then build in your model so you can move on to predict and act. And the transformation catalysts are not just about data availability and distributed computing. Then you need to build up the data science skill and do process and change management to actually use that. Oh, it's running out of time? Okay. So, I think I can stop here.
Talk up there is slow.
Thank you for coming.
Oh, thanks.
Appreciate it.
Oh,
That's
thanks.
a nice Berkeley hoodie.
Sorry, we